I wanted to talk about the method I use to determine enclosure size. Let's just refer to a ported or base reflex enclosure. The example I think is going to be sufficient for this application. Off of Parts Express, the GRS 12SW-4HE 12-inch subwoofer driver. Super entry level, $75 a piece. I think a very good value for the money, but this isn't a super high-end driver. But this is just a good example. So this driver is rated at 250 watts of electrical handling capability. 2-inch voice coil. I think it's roughly 12 millimeters of one-way excursion. Let's see what else matters to me. Oh, one thing I value this driver for is it has a low FS, which means it is happy tuned in a low frequency enclosure. They say 12.5 millimeters of excursion here. So let's take a look at my modeling software that I'm used to using. And so I've modeled 8 different enclosures, all to give you guys an example of this. This is how I go about doing this. So just for the sake of the conversation, one of these enclosures is only a half a cubic foot of internal volume. All the enclosures are theoretically tuned to the same 22 hertz tuning frequency. I just arbitrarily selected it. It happens to match the FS of the driver. Is that super significant? Not for this demonstration. So I'll show you on the graph. I'll zoom in on the graph and we'll go one by one and we'll talk about it. So let me zoom in here on this graph a little bit so that we can see it nicely. Okay, first enclosure is 0.5 cubic feet of internal volume. It models like so. This is also taking into account cabin gain of a vehicle. At the tuning frequency, there is a little bit of a dip. It's not got the peak that you would hope for. So how does a 1 cubic foot enclosure model? Get a little bit more output. Let's see, where is 2 cubic foot enclosure? As we go along, we're getting more and more frequency extension at the tuning frequency. Let's do 2.3 cubes. So this happens to be what Parts Express recommends for a ported enclosure. Where exactly they're getting that data from, I'm not sure, but this yellow plot line is what the enclosure size that they recommend. I'm not sure what tuning frequency they're claiming, an FS of 22 hertz. My modeling efforts, I wasn't able to, I don't know, it doesn't make sense what they're tuning to get an FS of 22 hertz, because most of these enclosures, the F3 that they're getting out of these enclosures, almost all of these on my modeling software is like 7 hertz is the F3. And I don't know if that's just because of the cabin gain or what. I really don't think that that's significant for this. The point I'm trying to get across in this video is the methodology that I use to determine the proper enclosure size. So let's model a whole bunch of different enclosure sizes and then evaluate them. So the next enclosure size I think we've got to model is a 4 cubic foot enclosure. This guy here. And then there's a 5 cubic foot enclosure. This guy here. And then there's a 6. I'm actually going to erase this and start over, starting with the 6th. I thought that it would model in a way that would give me visualization there. I guess it doesn't. Doesn't matter. We'll plot everything, and then we can talk about it. I've got to learn to be less long-winded. So looking at the amplitude response, the predicted amplitude response, the 0.5 cubic foot enclosure clearly does not have any extension. And then the larger the enclosure goes, the more we get an output at the tuning frequency. And we use a 6-foot enclosure. It's modeling that it would have a very, very high output. I don't know that that would be incredibly musical. It would be very peaky here, which may or may not be what you want. If we look at the cone displacement, how much the driver is moving for the 250 watts that it's rated at, the light blue trace is that 0.5 cubic foot enclosure. Clearly, that is choking the driver up, and the driver's having a hard time moving under the amount of power that it's going to be given. And with each increase in enclosure size, we are getting more excursion out of the driver, which means that the output is going to be higher. Vent velocity also increases. As we get more excursion, the vent velocity is going to go up because that much more air is being driven in and out of the port. So I think that there's something interesting to note here. It's not exactly what I would call a linear. With every incremental increase in enclosure size, there's something interesting about the difference between this enclosure's vent velocity and the two after that. So that's significant to me. And then cone displacement. Based on my experience with this Basebox Pro modeling software, I like to try and set up an enclosure that models at the peak above tuning frequency at 50% of the driver's maximum excursion. And if the driver's capable of 12.5 millimeters of excursion, I want to see 6.25 millimeters of excursion, which is this trace here. Again, this doesn't model, it's just not 1-to-1. I'm pretty sure that if we put this 12-inch driver in a 1/2-inch enclosure, that it's going to be far less excursion than this. So when I would usually say this software models conservatively, now I think it is over generating. It's exaggerating the amount of excursion that it will actually see. What I think is valuable is that with each increase in enclosure size, there's a point of diminishing returns. The amount of excursion decreases despite increasing the same incremental 1 cubic foot per enclosure. Somewhere between this pink trace and yellow trace, the point of diminishing returns is substantial. And then I would say we get roughly the same effect over here. Going from a 1/2 cube to 1 cube, substantial. Going from 1 to 2 cubes, pretty substantial. Going from 2 to just under 3, it starts to be a decrease. There's a diminishing return. And then the difference between a 5 cube, 6, let's see here, 4. Make sure I don't lie to you here. Okay, so the white, red, and green is a 4, 5, and a 6 cubic foot enclosure. The difference between those, the way it's plotted, is very little. So I just don't see the value in a 5 cubic foot enclosure or a 6 cubic foot enclosure when the 4 cubic foot enclosure isn't that different. So when I'm looking at a driver and not paying any real attention to manufacturer's recommendations or even just general rules of thumb I'm used to, I will quickly delete and remove these 3 that are way up here. The point of diminishing returns is high. I like the yellow trace and the pink trace, maybe the orange trace. I think it's a bit more realistic. I also think that based on the amount of excursion we're seeing, somewhere around this 6 to 7 millimeters of excursion is where we want to see, which is roughly half of the excursion limit of this driver. And honestly, I wish that it modeled exact. I wish that it told me exactly what real world was, but it doesn't. And so I'm going to delete, the 4 cubic foot, 5 cubic foot, and 6 cubic foot boxes, and we're just going to look at the we're going to look at the 3 cubic foot box, the 2 cubic foot box, and maybe the 1.5 cubic foot box. Although, like I say, I'm not convinced that this one's optimum. Yeah, we can delete that one too. I like this one, and I like this one. So the pink trace is a 2 cubic foot enclosure, and the yellow trace is a 2.6 cubic foot enclosure. The cone excursion is, they're claiming 7.5, 8 millimeters of excursion. And I think that that's roughly my experience, is that this will actually yield at 250 watts in those enclosure sizes, peak excursion. Like I said, my experience is that this is conservative. So I hope that this clears up at least the way that I conceptualize this. When I model something and I'm just kind of shooting in the dark, I'll model way smaller than is optimum and what I consider way larger than optimum, and I'll find where everything is in equilibrium, where our vent velocity is a usable vent velocity. The cone excursion, based on our power rating, is where we want it to be, and we get the best response. Did that make sense? Any enclosure that I try to model, I will I'll model a handful of enclosures that are above and below the right. That's how I find it. And the way that I do that is somewhere below the point of diminishing returns and somewhere above the obvious signs that the enclosure is, choking out the driver's ability to do its work. In the next video, I'm going to focus on Hoffman's iron law and try to represent how that graphs and what the laws of physics are doing when it comes to the restrictions or the difficulties of getting low frequency extension, the trade-off between loudness and low frequency extension. So we'll sign off for now. I hope that made some sense.